Okay, we're coming to the end of Chapter 5. Chapter 5 is the opening chapter in Calculus 2, which is integral calculus. In this video, we're going to go through section 5.5, which is on the substitution rule. And so as I've mentioned, one of the primary things that we learn how to do in all of Calculus 2 is we learn how to antidifferentiate functions, techniques and methods for finding antiderivatives of all kinds of functions, simple to complex. Now, I'm saying the term antidifferentiate, but as you might be aware of, people commonly don't use that term. Instead, people say that you're just integrating something. You're learning how to integrate something. In Chapter 7, we go through different techniques of integration. Integration by parts, trigonometric integrals, trigonometric substitution. They're talking about techniques to find antiderivatives. But as we've talked about at the start of Chapter 5, the term antiderivative kind of gets replaced by the term integral. And this is because of the fundamental theorem, because of the direct relation of antidifferentiation to integration. Okay, and with that, it's because whether or not you're evaluating an indefinite or definite integral, in both cases, you have to find the antiderivative. Okay, and so that's why, as I've mentioned, once we get into Chapter 6 and keep going into Calculus 2, I'm going to transition away from using the term antiderivative. I'm just going to say integration. Okay, but again, though, so one of the tasks of Calculus 2 is to learn how to find antiderivatives. And we officially started this process in the previous section, section 5.4. And we started this by, we were given a table of basic integrals. What basic integral means is it's just a single type of function on its own. So one of the types of functions that we're familiar with, like from algebra and trigonometry, just that type of function on its own. So there's not two functions, they're not multiplied by each other, there's not composition of functions, it's just one single type of function on its own. Or we were also given two properties. So if we could have two or more basic types of functions added or subtracted together, because we had the property. So this is, you can write this as, okay, and then there was also the constant multiple property. So if you could bring the constant multiple out front of the integral. So we could use these two properties with the basic integral rules. And that's where we started. And so we worked a bunch of example problems on basic integrals. And so now in section 5.5, we're just taking the complexity up a notch. We want to learn how to find antiderivatives, or in other words, solve integrals for slightly more complex functions than what we learned how to work in section 5.4. And to do this, we're going to learn the substitution rule. Okay, it says because of the fundamental theorem, it's important to be able to find antiderivatives. But our antidifferentiation formulas don't tell us how to evaluate integrals such as, so okay, here's the integral, the indefinite integral 2x times the square root of 1 plus x squared dx. And so, yeah, everything we learned in the previous section, the table of integrals and then the sum and constant multiple rule, we can't use any of that to solve this integral or find this antiderivative. Because, okay, we have two separate functions multiplied by each other, but there's no rule for separating the integral based on functions being multiplied together. Okay, we could use the constant multiple rule. We could take the 2 out, but that doesn't help us. We can't separate this based on a sum or difference, so from everything we learned in the previous section, we can't solve this. It says to find this integral, we use the problem-solving strategy of introducing something extra. Here, the something extra is a new variable. We change from the variable x to a new variable u. Okay, so it says we're gonna make a substitution here. We're going to change from the variable x to the variable u. And it says, suppose we let u be the quantity under the root sign. So what if we let u equal 1 plus x squared? All right, how does that help us? It says, then the differential of u is du is equal to 2x dx. So what does that mean? What are they talking about here? Well, all right, the first thing to point out is that they're using the term differential. They say then the differential of u is du is equal to 2x dx. And so what they're talking about is, here's u. right? U is equal to 1 plus x squared. And if we want to find the derivative of u, we can write it as du dx. Okay? Now, what is the derivative of u? It's x squared, so, or it's 2x. The derivative of 1 is 0, derivative of x squared is 2x. Okay? And so from here, you can think about multiplying this entire equation, both sides of this equation, by dx, and you're left with du is equal to 2x dx. And there you go, right? Now, a lot of people, and I know I did this personally when I was going through calculus, when I first learned calculus, the way I thought about this was like, okay, so yeah, du dx is equal to 2x, and this is like, this du dx here is just the definition of the derivative. You know, you just take a pure derivative of the function and you get 2x, and then you're multiplying both sides of this equation by dx, which is, you know, the infinitesimally small value, right? Because in the for the precise definition of the limit, there's a video around when we talk about the precise definition of the limit. I made a special video where we looked at the derivative through the lens of the precise definition of the limit, and it gave us a sense of what exactly dy over dx is. What is dy? What is dx? And the idea was that dy is and dx are infinitesimally small. If you don't know what video I'm talking about, I'll post a link to it in the description. But as large as infinity is as small as dy and dx are. That was the idea. Okay? And so that's what, you know, when I was learning calculus, when I was finding these derivatives to do these substitutions, and you'll see how we do that in a second, to me, I was multiplying by this infinitesimally small value here, dx, right? And we were kind of working with du and dx like they were numbers, like they were actual numbers. Okay, but the textbook is not telling us to look at it that way. The textbook, by the use of the term differential, what they're telling us is they still don't want us to look at it that way, as that du is an infinitesimally small value, just like dx in the definition of the derivative notation. They don't want us to look at it like that. They want us to look at du and dx like they're differentials. Okay, and so just to give a quick summary of what the textbook has said up to this point about Leibniz notation. So this is Leibniz notation, this idea of looking at a derivative like it's a ratio. Well, when we were first introduced to just the derivative as a function, we were introduced to the derivative, we were given a bunch of different notations for indicating find the derivative. So like f prime of x, capital D f of x, capital D subscript x f of x, all kind of different notations. And they called these all operators, and they said that we should look at Leibniz notation as strictly an operator, not a ratio, just look at it like it's an operator. Okay? And then we also talked about this Leibniz notation in regards to the chain rule. And it was stated that the Leibniz notation is very useful for understanding the chain rule in this sense. So if you have y is a function of u, which is a function of x, and you want to find dy dx, okay, then from the lens of Leibniz notation, it's easy to kind of remember how the chain rule works. You say dy du times du dx, and then that gives you dy dx. And Leibniz notation is useful because the textbook said if you treat these as actual ratios, then you could cancel the dus. But then but it said that's a useful way to remember the chain rule, but it says the textbook made it clear that we shouldn't technically think about it this way, though. You don't think about these as quotients. You don't think about these as actual numbers. Now, I do want to point out, though, if we come back to the definition of the derivative section, it did say here, it said the symbol dy over dx, which was introduced by Leibniz, should not be regarded as a ratio. It did say for the time being. So I'm not sure what they meant by that for the time being. I'm trying to figure out exactly what they meant by that. But so, I mean, this was the definition of the derivative. And in the section before this is section 2.8. In section 2.7, we were introduced to the derivative. What is the definition of the derivative at a point? In this section, we looked at the derivative as a function, so finding the derivative as a function of x, and they gave the different notations for derivative, for finding a derivative, including Leibniz notation. But they said Leibniz notation is just it's just a useful, interesting way of looking at the derivative as a ratio. But all of these you treat as operators, is what it's saying. Leibniz notation is a synonym for f prime of x. Leibniz notation is a synonym for any one of these, for all of these operators. But it did say for the time being. For the time being. Okay, and then it mentioned here this is one form of the definition of a derivative that's kind of synonymous with Leibniz notation. And then this topic of Leibniz notation didn't come up again until the chain rule section. And again, it said, so here's the chain rule written out using Leibniz notation. It says this equation is easy to remember because if dy over du and du over dx were quotients, then we could cancel du. Remember, however, that du has not been defined and du dx should not be thought of as an actual quotient. Okay? And then this topic of Leibniz notation didn't come up again after the chain rule until the differentials section, until this section, linear approximations and differentials. Okay? And what this was about was, so if we have a function, okay, and we know we can evaluate the function at a point, but then for whatever reason it's difficult or impossible to evaluate the function off of that point. But we could estimate the value of the function near the point using a linear approximation. So with the equation of this tangent line to the point P, we could use this tangent line to approximate the value of this function in blue near the point. And so to do this, what they laid out here was that, the notation here, they said that, so delta x and delta y are associated with the actual function, the function in blue. So you move delta x in the x direction, it's positive here, and then with that delta x, the function, to get back to the function in blue, you go delta y. But from the equation of the tangent line, from the tangent line approximation, instead they used dx like this. So you go dx, but dx is the same as delta x because you're kind of picking how far you want to go from P. But then dy is going to be different than delta y. The dy is to get back to the tangent line approximation. That's going to be different than delta y. And it's this dx and dy that they called differentials. And the notation is like that Leibniz notation, because what the textbook did was they said, okay, to get this tangent line approximation, what you do is you find dy dx, and so the function is y is equal to f of x, so dy dx is f prime of x. Okay, then you multiply both sides of this equation by dx, and there you go. There's dy is equal to f prime dx. Okay, but what you want to notice here, though, is that when you multiply both sides by dx, you're not really multiplying by that infinitesimally small value that is associated with the definition of the derivative. In this context, you can see dx and dy are more of like normal size numbers. Like dx could be 0.2. dy, I mean, they give examples here. I mean, yeah, they solve for dx and dy. Dx could be like 0.2. dy could be 0.7. Okay, so the point I'm trying to make here is if you're using the term, if you're referring to dy or dx using the term differential, then you've kind of gotten away from that infinitesimally small description that's associated with the definition of the derivative, okay? And so I wanted to point that out to make this very clear. So we want to solve this integral. We can't use it with the traditional methods from the previous section. to do this, they're saying that we're going to make a substitution that u is equal to 1 plus x squared, under the integral sign. In that case, then, it's saying the differential of u is du is equal to 2x dx, which they got from this process here. But again, just don't think about it, though, as you're multiplying, that you're not thinking about dx and du as coming from the definition of the derivative Leibniz notation. You're thinking about it in the context of the differential, okay? And so what happens, though, okay, so with that in mind, just keep that in mind. And so it says that, so notice that if the dx in the notation for an integral were to be interpreted as a differential, then the differential 2x dx would occur in equation 1. And so formally, without justifying calculation, we could write, what are they saying here? Let's come back. They're saying that it says if the dx in the integral, so this dx here, if you were to interpret that as a differential, okay, if you were to take that step and interpret this as a differential, then this du, this 2x dx, would occur here, this 2x dx. And so you could substitute 1 plus x squared, you could substitute that with u, and in 2x dx, you could substitute with du. And you're left with an integral that's been simplified, and we can, based on what we learned in the previous section, we can solve this. Okay? Now, I want to make sure you wrap your head around the Leibniz notation, the use of differentials. And so, but like in the definition, whenever we define the integral in, I think it was the definite integral section and the fundamental theorem section, we went into detail about what all of this means. Okay, the dx, I mean, all of this notation came from the definite integral. This notation was taken from the term integration. The idea of integration started with a definite integral. And then once it was found that the fundamental theorem, there was this association with anti-differentiation, they brought all of this notation to be used to indicate anti-differentiation. So, but in the definite integral, this s symbol, this dx, it came from it was the infinite summing. The limit as n went to infinity, okay, f of x dx was f of x star. Okay, the limit as n goes to infinity of the sum here, this is where the s symbol came from. The s symbol replaces the infinite sum. Okay, the f of x, the f of x is just the function, and then, well, no, this wasn't dx, this was delta x in the actual sum. Okay, this was delta x. Okay, now, but as n goes to infinity, we know delta x is equal to b minus a over n. Delta x gets infinitesimally small, and so the delta x gets replaced with the dx. Okay, but so the dx is, this, as far as the definition of the integral, the dx is absolutely infinitesimally small in the same way that for the definition of the derivative, you could think about dy and dx as being infinitesimally small. But however, they're just telling us, as far as for this substitution rule, they're telling us that we're gonna find the differential. So what this is really important. I want to make this clear. They're telling us that if we want to look at this, if we want to be able to take a derivative du dx is equal to 2x and multiply both, and think about multiplying both sides by like dx, then it's saying we need to think about this as a differential. That's what the textbook is telling us, at least at the moment. We might get new information as we proceed, but at the moment, they're saying you cannot think about these as infinitesimally small if you're going to be multiplying both sides by dx like this, if you're going to be making substitutions like this. We have to think about du and dx as differentials. We have to think about dx here as a differential. So that's what the textbook is telling us. And so you make the substitution, you get the indefinite integral square root of u du. We can solve that. Once you get the answer, substitute back in for u, and here's the result. Okay, so here's like a proof of the substitution rule. And then they give a formal definition here. It's saying if u is equal to g of x is a differentiable function whose range is an interval I and f is continuous on I. So, yeah, so u needs to be differentiable because we're going to be taking its derivative. And then the range of u needs to, like, if we come back here, if we're going to substitute u is equal to 1 plus x squared, you can't have the interval that we're working with u on violate the domain of the range of that violate the domain of the square root. So it's just saying that, you can't have this is like math, technical math talk here, saying that it's a differentiable function whose range is an interval I and f is continuous on that range. Then if you can write it as the function or f of u, right? So you've replaced the x expression with u, with this g of x is u, and then the rest of it is g prime x dx, that differential du, then you can rewrite it like this into the simpler form here that is, that, if you set it up right, is going to be solvable. Okay, so now it says, notice that if u is equal to g of x, then du is equal to g prime of x dx. So a way to remember the substitution rule is to think of dx and du in 4 as differentials. Then the substitution rule says it is permissible to operate with dx and du after integral signs as if they were differentials. So what are they saying here? So, I'm going to do the best I can to try and translate what they're saying. To me, they're kind of dancing around the issue here. Everyone, in my opinion, has questions about how do we view this in integrals, the dx, and how do we view in derivatives dy over dx. It's saying here that the substitution rule tells us that it is permissible to operate with dx and du after integral signs as if they were differentials. So to me, it's treating dx and du like this is a powerful statement, okay? Because we know in the actual integral, for the definition of the integral, okay? So an indefinite integral, okay, and then that's a definite integral, and then an indefinite integral, okay? As far as the definition of the integral, dx is infinitesimally small, in the same sense that infinity is infinitesimally large. That's what the definition of the integral tells us. It says here, to me, this is what I glean from this, the substitution rule. So they proved the substitution rule here, okay? And it's saying that what we learn from the substitution rule is that it is permissible to operate with dx and du after integral signs. So to me, they're referring to these as these are infinitesimally small, like the actual integral sign dx or du or whatever, d whatever. We can operate with them as if they were differentials. So we can, even though we know that dx and du are infinitesimally small, we can operate with them. We can treat them like they are differentials. So we can treat them as numbers. Okay, so this is really interesting. I'm hoping this is helping to shed some light for you on Leibniz notation and these dx's and dy's for derivatives and in integrals. Okay, so that's the substitution rule. We're going to work a bunch of example problems so you can get the hang of this, but let's just take a quick look at some of these examples. So here, we can't solve this with the basic methods, but if we say, what you're looking for is you want to make u be equal to some expression of x in the function, not the entire expression. A piece of the expression in the function is you're going to make equal to u. And the idea is when you take that derivative of that u, the resulting differential du is the rest of the function, including the dx. And so you can end up replacing all x values. So you can see here, we know the derivative of x to the fourth is something x cubed. Okay, so if we say u is equal to x to the fourth plus 2, because we want to replace everything inside of this cosine. And we know that's no problem because the derivative of the 2 is 0. You get du is equal to 4x cubed dx. Okay, now, but wait a minute. We don't have 4x cubed dx. We have x cubed dx. Well, okay, you can divide both sides by 4. You have du over 4 is equal to x cubed dx. So you replace x cubed dx with du over 4. You see? So if we come up here, right? So you get cosine u, because we define u to be x to the 4th plus 2, times 1/4 du. So you just bring the 1/4 in front of the integral. And there you go. Cosine u du, we can solve that. Is the integral of cosine u du is sine u plus c, and then you just substitute the u back in. Okay, here, if we substitute u is equal to 2x plus 1, then du is equal to 2 dx, so dx is 1/2 du. And so you're left with the integral of the square root of u times 1/2 du. Bring the 1/2 out front, and there you go. We can integrate u to the 1/2 power of the square root of u. No problem. Okay, here, if we substitute u is equal to 1 minus 4x squared, that derivative is, it's like an x dx, some form of an x dx. It's the du of 1 minus 4x squared is minus 8x dx. So solving for dx, the dx is minus 1/8 du, which works. You just have this coefficient of minus 1/8 that you can bring out of the integral, and so you're left with, after making the substitution, you're left with minus 1/8 times the integral of 1 over root u du, and you can solve that. Okay, and so that's the idea, and there are more complicated examples, but we're gonna work a bunch of these problems so you can get the hang of all of this. All right, so next it talks about definite integrals. So doing substitution with a definite integral. Okay, we just looked at indefinite integrals. And so the one thing you might be thinking is, well, what's the difference? You have a definite integral, find the antiderivative, just like we just did. And then once you have the antiderivative, just do the antiderivative evaluated at the upper limit of the integration minus the antiderivative at the lower. And yeah, you could do that. That's fine. Like what I mean is, if we come back here, so okay, we just saw how to solve this, right? You know how to solve this using substitution. And so, okay, if this is an indefinite integral, if this is going from 5 to 2, well, whatever, just do the exact same thing we did, find the antiderivative, but now you're instead of finding that antiderivative plus c, you're going to put into the capital F of x, you could do capital F of 5 minus capital F of 2. And you could do that. That's fine. But it says here, there's another method which is usually preferable, is you can change the limits of integration when the variable is changed. And so what you do is you have a definite integral, and you need to use substitution. And what it's saying is, when you substitute for the new variable u, so you find u, then you get the differential of u, and then you make the substitution. So now you've eliminated x, the x variables in the dx, and you have just u and du. Well, what you could also do is, at that moment, you could change the limits of integration to go with that variable change. And what they're saying is, what you do is, to do this, you have your u is equal to whatever, 1 minus 2x squared or whatever. You plug in those limits of integration. So like if you define u is equal to 2x plus 1, and the original limits of integration a and b were, 3 and minus 1, then you would change minus 1 to, it would still be minus 1, and you would change 3 to 7, because, okay, 2 times minus 1 is minus 2, plus 1 is minus 1. But then, so you'd leave minus 1 as is, that's a coincidence, and then 3 you would change to 7. And then what do you do from there? Then you get the antiderivative based on u, the variable u, but then you don't have to, once you get the antiderivative based on the variable u, you don't have to, at that point, for a definite integral, you don't have to switch back to the x variable. You can just do the f of capital, the capital F of u at the new limits of integration, and you get the same answer, right? So you get, so here you've gotten to this point. You made the substitution. You've updated the limits of integration. Now you find the antiderivative, capital F of u, but you don't have to switch back to substitute the u back in here. You could just do the subtraction just like this. F of the new upper limit of integration, capital F of the new upper limit of integration, minus capital F of the lower, the new lower limit of integration, and you get the same answer. Okay? And so here's some examples. We're going to work a bunch of examples. Okay. Now, the last thing that this section talks about is symmetry. The next theorem uses the substitution rules for definite integrals to simplify the calculation of integrals of functions that possess symmetry properties. So yeah, it just uses the substitution rule for definite integrals to prove these symmetry properties. But what they're talking about here is, we've gone through this in algebra, but so there's the graph, so you have like an equation that's, in general you have equations. When you talk about graphs, like you have a circle, right? The graph of a circle, that's an equation. It's not a function though, right? So you've got, but so just thinking about general graphs, just functions and non-functions, there's the symmetry, the potential symmetry is symmetry about the x-axis, symmetry about the y-axis, or symmetry about the origin. But if you're restricting to just functions, there is no symmetry about the x-axis. There is the trivial case for the line y is equal to 0, but in general, there's no symmetry about the x-axis for a function, because then it's not a function. You can only be symmetric about the x-axis if you've got more than one value above and below the x-axis. That's not a function, okay? So when it comes to functions, the only options are symmetry about the x-axis or symmetry about the origin. And all that means is that the symmetry about the x-axis is just saying that if you have, for any point x comma y on the graph, if you multiply that y coordinate by -1, or no, it would be if you multiply the x coordinate by -1. So it's symmetric about the y-axis. If you multiply the x coordinate by -1, then you're still on the graph, right? You see how that would work? If this is x comma y and you multiply just the x coordinate by -1, you're still in the graph. That's symmetry about the y-axis. In that case, you have an even function. It's what's called an even function. And you test for an even function if f of minus x is equal to f of x, the original function. If you plug in minus x into the function and you simplify and you get back the original function, that's symmetric about the y-axis, and that's called an even function. Okay, the symmetry about the origin means if you have a point x, y on the graph, and you multiply both the x and the y coordinate by -1, you're back on the graph. So you multiply the x coordinate by -1 or the y coordinate by -1 and the x coordinate by -1, and you're back on the graph. You have to do both, not just one. Okay, that's symmetric about the origin. That's what's called an odd function, and you test for an odd function by, you see, is f of minus x equal to minus f of x. Okay, so that's a quick review of symmetry of functions. All right. So how do these type of symmetric functions relate when it comes to definite integrals? Okay, so it says, suppose that a function is continuous on the interval from -a to a. Then if f is even, then you can simplify this definite integral by changing it from 0, the limits of integration from 0 to a, and bringing a 2 out front. And this makes sense. This is common sense because, okay, here's an even function. And let's say this is -a to a. Right? The definite integral is the area under these two curves. Well, you can just find the area under this curve and multiply by 2 for an even function. Okay? So that's a property for a definite integral property for even functions. What about an odd function? Right? Okay. Oh yeah. And so, and you can see it says that an even function is f of minus x is equal to f of x. That's how you test for it. It's symmetry about the y-axis. All right, what about an odd function? So an odd function is symmetric about the origin. F of minus x is equal to minus f of x. An odd function, the integral from minus a to a of the odd function is equal to 0. All right? So does this make sense? Yeah, so if, a to minus a, since it's an odd function, it's going to be this area minus this area plus this area, and it's going to be the same area because it's an odd function, because for any point x, y, you multiply those points by -1, and you're on the graph. So it's that symmetry about the origin means that you'll have these equal areas on the left and right side of the origin. So as long as you're going from the limits of integration are the same distance relative to the origin, then integrating an odd function like this is going to be equal to 0. Okay. So that's the substitution rule for evaluating integrals in general, antiderivatives, but also we talked about how you treat definite integrals with the substitution rule, and then also functions with symmetry, even in odd functions, in relation to definite integrals.